In time-critical scenarios, such as emergency evacuations, first responder prioritization, and crisis management, decision-makers must act quickly and effectively. They need to rapidly select among multiple spatial targets, such as choosing between exits to guide crowds, developing personnel rescue plans, or identifying areas that demand immediate attention. Recent advances in artificial intelligence and indoor sensing offer new ways to support these decisions. Existing methods commonly employ 2D maps to display data and AI suggestions. However, mentally mapping this information onto the real world imposes a significant cognitive load. This burden can impair users' ability to critically assess AI suggestions, resulting in inappropriate reliance. In contrast, embedded visualizations in augmented reality directly integrate and display data and AI suggestions in physical environments, thereby reducing the cognitive load of mapping and fostering more deliberate and appropriate reliance on AI. To assess this, we pointed out our research question: can AR embedded visualizations foster appropriate reliance on AI in spatial decision-making? We designed a task where participants had 20 seconds to choose one of 4 coffee machines across 2 floors. Their goal was to get coffee as quickly as possible. To make the best choice, they had to consider 2 key factors: walking distance and queue length, and AI can suggest the choice for reference. This setup demonstrated a time-sensitive decision-making scenario in a large-scale spatial environment. It allowed us to study how AR-embedded visualizations influence user judgment on AI suggestions in a realistic but controlled setting. 32 participants were recruited for the study. Participants completed the tasks using 2 types of visualizations: a 2D minimap and an AR-embedded visualization, X-ray. The 2D minimap showed a top-down layout of the 2-floor office, with each floor presented separately. The AR X-ray provided a 1-to-1 digital twin of the space, embedded directly onto the physical environment. AI suggestions would be highlighted in blue in the visualizations. Participants were counterbalanced by the order of 4 conditions: minimap without AI, minimap with AI, X-ray without AI, and X-ray with AI. Each participant completed 36 trials, 4 training trials followed by 32 task trials. We created 32 unique spatial arrangements of the coffee machines, varying across 4 difficulty levels based on floor layout and proximity. These we grouped by 8 participant locations. At the start of each trial, a 20-second countdown began. As soon as participants decided, they verbally indicated their choice, such as target D. The experimenter then stopped the timer and cleared the display. Afterwards, participants rated their confidence on 1 to 7 scale and pointed to the spatial location of their selected target in the real world. This process repeated for each trial. We collected both quantitative and qualitative data, including decision accuracy, response time, reliance metrics, self-reported confidence, point error, and post-study interviews. Our results showed participants were more accurate in the minimap condition than in the X-ray condition. Participants relied on AI more inappropriately in X-ray compared to minimap, primarily as over-reliance. Participants in the X-ray with AI condition spent less time on decision-making than in the minimap with AI condition. The X-ray visualizations significantly improved participants' spatial mapping abilities compared to minimap. Participants felt equally confident in their decisions regardless of visualization type or AI assistance. An analysis of the post-study interview shows that participants considered more on spatial reasoning during decision-making in the X-ray condition. This indicates that the AR X-ray visualizations inherently facilitate spatial perception. The X-ray visualization led to greater participant trust in and reliance on AI suggestions compared to the minimap. In conclusion, our study outlines the lessons learned, design implications, and promising future directions for better harnessing these AR strengths to foster human-AI collaboration in spatial decision-making. Please see our paper for more details.